Okay, I'm Kevin Gero. I'm one of the co-workstream leads for power distribution immersion from Murata.
Hello, good afternoon. Thank you for coming. My name is Oriol Chavanel. I work at Submer, and I'm a technical alliance manager and OCP lead.
So what we're going to talk about today is OpenRack V3 for single-phase immersion tanks. That's what we decided to focus on. And what we're doing is we're creating a base specification. The idea is to produce something that if people follow that, they can then put together a immersion tank with power, with ORV3, and should be just fine.
So yeah, on this first slide, we just explaining very basically what we have been looking at since the beginning of the creation for this work stream. So basically, we just took the vertical racks that we can see there. As you can see in the left, there is an immersion tank, and we tried to replicate the open rack version from air into the immersion tanks. These are single-phase immersion tanks, sorry. So basically, we took the similar name of use that a vertical air rack has for data centers, and we tried to replicate it into the tank by adding also the busbar in the bottom of the tank, by respecting the organization and the positivity of the electricity, so positive and negative in the both sides of the busbar, and replicate it from left to right into the immersion tanks. On the features, as I was mentioning, we have the tank, or wood enclosure, as we call it for the requirement. We have also the busbar, which is sitting in yellowish at the bottom of the tank. We have the power shelf that is adapted for immersion in this case. We have the power supplies, which are also revised and adapted for immersion, and the fluid or the coolant, which is the environment that is connecting everything together. So as a requirement for the tank, on the highlights we have that we need one or more busbars in immersion. One of the benefits of single-phase immersion here is that we can run up to 3 busbars in the immersion tanks. The busbars are located in the bottom of the tank where the fluid typically is pumped, so it's a very cold environment where we can pull more from those busbars. Those are ORV3 busbars, not HPR, so with the amount of copper they have and just sitting in the bottom of the tank, we can go like 2 or 3 times the kilowatts that the busbar can hold in air in a normal air rack. And then, well, all of the tank structure that is designed to be complying all of the requirements that we designed into the immersion work streams. So like the different spaces to hold the weight of the servers and the power shelves laterally. And then other things about the busbar polarity to define where the positive and the negative is located, right? Also to mention, the busbar temperature rise has been tested in different environments where we brought a hike like more than 100 kilowatts into those busbars, and there is not more than 5 to 6 Celsius increase on the temperature rise. We made a limit with all of the community agreement on 30 Celsius in the worst case scenario, which is still very manageable. This is just an image of what I was just explaining. So this is an image of the bottom size of the tank, so you can see that there is the busbar sitting in the center. There is also 2 more in the laterals in case of necessary. Those can also be adjusted for redundancy. There is some power shelves that the clip can go to the right, in the center, or to the left, so you can select which busbar and which power shelf you will be using inside the tank. But basically here you can see how the power shelf is leaning, is stopping into the lateral stoppers, so the weight is not relying into the busbar, but on the tank, and it's easily connecting into the center. So the same happens with the servers, and so on. This is also a picture about the definition of the polarity I was mentioning before. So typically the positive is always in the rear side of the tank, and the negative is in the frontal part, to just make clear how the positioning of the servers needs to be inside the tank. In a vertical air rack, it's very easy to identify how to install a power shelf or a server. In an immersion tank is not that easy. You can confuse. You can maybe install it in the other way around. We are now also working on the spec to add a mechanical stopper that can avoid that there is a misinstallation of a server or of a power shelf that can lead into a short circuit because it's in the other way around. So this is part of the spec that we will release at January 2026, we hope so. And back to Kevin.
So the power shelf, the basics of the power shelf shall be needs to have handles. If you're in an immersion tank, you have to be able to lift it out. So it's a requirement. Some would think, oh, that's common sense, but we want to make sure we've got it covered. Also, we don't want the power shelf to be more than 4 OU in a single unit. 4 OU is pretty big. The one example we've done is 3 OU. If it's 4 OU and you put all those power supplies in, it gets pretty heavy. So anything more than that, we're saying don't do that. The width of the power shelf is there to allow secure attachment to the rails. So basically, we're following the OCP rack power spec on those dimensions. Initial testing of the bus bar, as we said, allows for very, very high current with a small thermal rise. Obviously, most of you folks understand immersion. It's really nice that you can take less copper and get 2 or 3 times what they get in air with the immersion tank. The AC input connectors and controller are required to be above the fluid level. That's for 2 reasons. One is for access by the operator, and you don't have to put your hands in the fluid. Number 2 reason, and even more important, is you can use standard AC input cords and connectors. If you had it where it was below the fluid, you would have to have a seal on the AC cord so you didn't get capillary action. So it's one of the requirements that we put in here. The weight of the power shelf, again, must be supported by other than the output connector. Of course, you don't want all that weight sitting on that connector. So there must be another way. As you saw in the previous image, we show how you can do it by having feet on the side. That's not the only way to do it. There are other vendors that put the bus bar down in a trough, and so there is a surface that it would sit down flat. How you do it is not been defined. What is defined is you must do that, so it's not sitting on the connector. When using a single-phase input supplies, or with 3-phase Y input, this should be groups of 3. The idea there is so in a Y configuration, they're balanced, and that way you don't get neutral currents. So again, this is what OCP has done in the rack power up to date with the single-phase power supplies, and we wanted to keep doing the same thing. It just makes sense. That way the neutral line isn't carrying a lot of current, and you don't have any problems. And the recommended power placement in the tank. Okay, what we're showing here is that if you put the power shelf in the center of the tank, half the current goes one way, half the current goes the other. Therefore, only half the current is flowing through the bus bar at any one given time. If you put it all the way at the end, then it has to handle the whole amount of current through the whole bus bar. So of course, that's twice the current than you did if you put it in the center. So optimal from a power standpoint would be to put it in the center of the tank. Now, as long as the bus bar can handle the current, be my guest, put it at the end. We're just pointing it out so people understand that this is what you're up against.
So about the safety side on the things and the standard that we have been looking, I think before they were already mentioning this many times. There is the UL 62368-1. This is based on the specification about insulating fluid into media equipment in immersion tanks. So this is one of the standardizations that we try to follow for safety guidelines. There is other things that we have been taking from the immersion requirements. There is other things that we are learning from ASHRAE and other institutions. So basically, we have been defining into the spec some of the things that we have considered into the community. For example, one is the coolant level that we need to monitor in the tank to protect, at any case, any short circuits, any component failures that are not being cooled down that can create a fire situation, for example. Condensation is another of the topics that we have been also raising up, that on the ambient temperature that we have in a data hall is very important, and sometimes we are not considering that when deploying immersion tanks. And moreover, there is also a mechanism that have that have to prevent an enclosure design that be having a locking. With this, we mean that we need to be able to be sure that we can lock a lid, an enclosure from an immersion tank that cannot be opened by any operator and cause also a situation in a data hall, right? So those are just a few points that we have been discussing into the work stream. There is also some others about the safety components that have to be tested and verified. There is not a lot of references sometimes in the market, so we are trying to work also with the FMEA, as Amy was explaining, and Andy as well, to understand what a failure in a power supply unit in immersion, a spark plug that can happen inside the fluid, if that is affecting the auto-ignition point because it's becoming too hot. All of those things are very connected to the fluid requirements that we have been checking into the work stream. So all of the information that has been put along, it's checked with material compatibility, with FMEA, and other elements of safety. And I think last to mention, I wanted to say that there is a period evaluation that we say quality and integrity. So for the different proposals that we have been receiving into the work stream to test a power shelf, a power supply in immersion, in the worst case scenario, we replicated a proper test in one of the facilities of the participants to understand what it will happen, what it will take, and if it will affect the safety or the lifespan of the product. So this is what we're trying to come up with here and release the base spec.
And for the power supply, we wanted to put some safeguards in place, some things that, quite frankly, are in most every power supply, but we wanted to point them out. It protects not only the power supply, but it protects the system. So DC output over voltage and over current protection seems like it makes sense from a power standpoint. We always do that, but it's important. If you do that, then you limit problems that can happen. Obviously, if you lower the current, keep the current below a certain level, then you're not going to have problems with the fluid in the tank. Over current protection shall include over power protection. So it's something that should be in a power supply anyway, but we're pointing it out. Please do it. It keeps us out of trouble in the long run. From a power supply standpoint, we do that in a power supply because, quite frankly, it protects the power supply, but it also protects the system. AC input over voltage and under voltage protection. If the voltage was too low and you allowed the power supply to run, then the currents would go very, very high. So you have to do that. Over voltage, you don't want that over voltage to end up damaging product, so you have to have some kind of protection. Over temperature warning and protection. Now this is very, very critical because if something happened in the tank and the tank didn't have cool fluid coming in the bottom, what would happen? Well, the temperature would start to rise, right? So if the temperature gets above a certain point in the power supply, we have thermal shutdowns, so it would simply shut the power supplies off. And it takes care of that for us. Now in the tank, they have similar protections, but so we have belts and suspenders here. We have the power supplies takes care of it, and the tank takes care of it. Each one of the, as we just said,
So just to close up, we want to make a bit of call to action. The base spec is about to be closed and to be released, but we would like to keep improving always what we have been working in the work stream. So any electrical engineer, any requirements from any tank or enclosure providers, anyone that is a fluid expert, several vendors as well, please join us, participate. We have defined this, but there is more to come. We want to increase in density. We want to increase in a more efficient environment each time. So anyone who wants to join the calls are the second Wednesday of every month at 5 p.m. European time or like 8 a.m. in America, depending on the zone, of course. But please join us. We are a very cool group, and we are discussing very cool stuff, so we would like you to be part of the next specs coming up. We want also to give a special thanks to Nick from GRC that has been a very good help on the last months to release this further. Also to Tim from Foxconn and some other fellas that are not here today, but that have contributed a lot to make this happen. So thank you. I think we are time up. So if you have any questions, Kevin and I will be happy to answer them.
Thank you very much.